This is the second video on combined loads. This addresses after we've decomposed loads into the various types of loads, how do we test for failure in these loads? So the overall process for combined loads is to decompose the external loads into axial, torsional, and lateral loads, which we did in the previous video. And here we'll learn how to calculate the internal loads due to each, calculate the stresses due to internal loads, and that we identify all positions of interest where any of these stresses are extreme. So there may be one or more locations for each type of load. So we may have quite a few more locations of interest with combined loads than with single classes of loads. After that, we superimpose all the stresses at each location of interest. We do stress analysis after superposition. This is a very key order: do superposition, then stress analysis, and then we compare these to the ultimate or allowable stresses. So take a moment to clarify the property of superposition. So this property of superposition says that if you have a response such as stresses in an object caused by multiple perturbations, here loads, then the response to those is the sum of the responses to individual perturbations. So the property of superposition only applies to linear systems. Now, stress is linear with respect to load, so we can superimpose stress. Deformation is just the integration of strain, which is linear with stress, which is linear with loads. Integration is a linear property, so we can superimpose deformations. The caveat about this is that the loads must not interact. What that means is if there is a large deformation, then this would change the direction at which other loads are applying, and therefore the loads would interact. So essentially, this requirement of not interacting is the same as saying that there have to be small deformations. But it's a more restrictive definition of small deformations that we dealt with before, because, for example, on twist angles, we didn't worry if they twisted into a large angle if we were drawing the torsion as independent of where the force was applied. So we know how to calculate from these individual loads. We know how to go through and calculate the stresses due to the loads, but superimposing the stresses caused by each type of load can present a challenge. And so let's look at this here. And the reason it can present a challenge is because we need to align the coordinate axes. What do we mean by the different coordinate axes? So if a beam is in the x direction, we'll take as the example here, then our axial stress n of x results in sigma of x. And of course, this is equal for all y and z. It might vary in x, but it's the same across the cross-sectional geometry. A torsional stress results in tau x theta. This is complicated by the fact that theta can be in the yz or anywhere in the YZ plane, depending on the position being considered. We know that tau is maximum at the surface, but the question is what part of the surface. So I'll just show you at an end so it's easy for us to see where we are. If we're looking at the tau x theta here, we're looking at this. So then tau x theta, what we see is that theta here is like the y direction. So in that case, what we have is tau xy. But if we're here on the top of the beam, that element is flat here. It's going straight into the z plane. And so up there, tau x theta is actually tau xz. And then back over here, it's again tau xy. And over here, it's again tau xz. Now, somewhere in between, it's really neither of these. It's something else. But fortunately, we usually only have to consider these four locations: the front, the back, the top, and the bottom, because here it's the same everywhere, and all of the other stresses that we consider are either the same everywhere or extreme in the midpoint, the top, or the bottom. And so it's just those 4 points that with torsion we'll have to deal with. Now, if we have bending moments, such as m of x, these also result in a sigma of x. And we learned already that these are maximum at the top and the bottom of the bar. And that's where, so that's at those places we'd have to consider, at the top, we'd have to consider sigma x due to the longitudinal bending moment, maybe sigma x due to the axial, so we'll call this sigma xa, we'll call this sigma x longitudinal because we referred to those stresses that way in a lateral, or you can also think of that as sigma x due to a lateral load. So we have to consider all three of these at the top and the bottom of a beam. At the front and the back of the beam, we will have tau xy from the shear force from the lateral load and tau xy or tau x theta from the torsional load. So we will have these two as sources, tau xy from lateral and tau xy from torsional at the front and the back of the beam. As well as in those locations, we will also have the sigma x from the axial will show up. But of course, the sigma x from lateral is 0 at the midpoints. So these are some of the complications of, I already addressed that, of dealing with adding these together. But once we've identified the coordinate axes, and it's useful to say at each location, put them into x, y, z coordinate axis, getting rid of those thetas so that we are using the same coordinate system. Then all we have to do is add the Cauchy stress tensors. So the key thing when we add the Cauchy stress tensors is not only do we only add a sigma x to a sigma x, it could be sigma xa or sigma xl, doesn't matter, they're the same direction. It could be a tau xyl or tau xyt, it's still tau xy. So we add the stresses in the same direction, the same types of stresses. We also have to make sure we are only adding stresses that occur at the same location of the beam. We cannot superimpose something taken here with something here. We can't superimpose something here with something down here. We can only superimpose places that are the stresses due to all the types of loads at a specific object. So superposition means which positions are interest, calculate all of the stresses due to all of the types of load at that position, and then add the Cauchy stress tensors. And we do this for every position of interest. So once we have performed the superposition, then we do stress analysis. And again, we do this at every location of interest. So every of our new added together Cauchy stress tensors, we do stress analysis. Now, in a lot of locations, we still have pure torsion and pure axial, but not everywhere. Fortunately, there is still most of the time plane stress, and if that's the case, we can still use R and sigma average to calculate the principal stresses. And then don't forget out of plane shear stress when we find tau max, but all of those are what we've dealt with before with plane stress. If we ever end up with one that's not plane stress, we use the eigenvalue method. And again, consider all three choices of tau max. And we can call with that one sigma 1 to be the largest eigenvalue and sigma 2 the smallest or possibly most negative eigenvalue. So over all these positions x, y, z, we compare what is the maximum of the principal stress at any of those locations, of the principal stress number 1 at any of those locations. Is that less than the ultimate tensile stress? What's the minimum of the negative of principal stress 2 at all those locations and compared to ultimate compressive stress? And finally, we can ask the maximum of tau max. That is, tau max was the rotation to find the maximum shear stress at any coordinate system at any location, and the max here is the maximum overall locations. So we can compare then, that allows us to get the most shear stress anywhere in the object, and we compare that to the ultimate shear stress.